Hi, this is the video game tutor, and I'm here to go and help you guys learn about something really cool, how to use the residue theorem. Basically, the way to use this theorem is pretty simple. Let's say you've got something like a contour integral, right? And you want to solve that integral. All you need to do is you need to take the residues inside whatever contour you're solving in and add those residues up, and that actually will give you the inside of that integral. So, let's say you've got something like this, right? And you have an upper half sphere, and you have residues over here and here, and even if you're interested in this part, all you gotta do is show that this part goes to 0, this arc on top, and that this real axis on the bottom here will actually be your answer of what the residue becomes. So, how do we do this? How do we actually use it? Let's do an example of this. So let's say we're solving for the residue of the contour integral over 1 over something like x squared plus 1. So, actually let's not make it the contour integral because we'll turn it into the contour integral later. It would be better to go and use this as just a regular integral from negative infinity to infinity, right? Okay, well, how do we actually use this, right? How do we actually solve this? Well, let's see over here. On the bottom, we can split this into x plus I. Sorry about that. Times x minus I, right? So these two factors will show you the poles of the system. The poles is basically where the thing explodes to become undefined. So where the denominator is 0, right? So for here, when x equals negative I, that would give you, that would be a pole. And here when x is equal to positive I, that would also be a pole, right? So how do we use that? So first, we should talk about what the residue theorem actually is. So the residue theorem basically states that um, if you have to take an integral of f of z dz and it's a contour integral over some contour on the imaginary plane, right? Basically, all that matters is it'll be 2 pi I times the sum of all the residues of that function at certain points where it blows up. So how do we find these residues? So there's two methods that you should know. The first, well, there's technically three, but two main ones that are important. The two methods are the first method, which works for all multiplicities on the bottom. By the way, multiplicity just means if this was squared or cubed or something, that would be multiplicity 2. Basically, the residues of f of z at zk is equal to phi to the m minus 1 over m minus 1 factorial. But what is phi, right? Phi is basically the part that we don't use. So what does that mean? So if we have something like 1 over x plus I, x minus I, then let's say we're solving for the residue at this point, at positive I, phi would just be everything else. It would just be this part over here, this part of the function. So if you had something like 1 over x plus 1 or whatever on the bottom squared, phi would just be this part. It would just be I. It would just be, it would just be 1. But if you had something like e to the I x over x plus I x minus I, again, and you wanted to solve for the residue at this point, the phi you would use is just this part over here. So basically, so m is going to be the multiplicity of the pole, right? So it would be how many derivatives you take minus 1 over m minus 1 factorial. And then what you would do is you would take this, what you get over here, the solution, and you'd plug it with zk, which is the pole you're solving for. And then the second method, which works specifically if the pole is multiplicity 1, is basically, let's say you have a function f of z, and the top is pz over qz, and pz is not equal to 0, qz, and remember this had zk, this is the specific pole, right? This is the specific pole you're solving for. Qzk is equal to 0 at that specific pole, but q prime of zk is not equal to 0, then what happens is that the residue in method 2 will just be equal to pz over q prime of z. Okay. So let's use an example to show what I mean. So let's solve what we were solving for before, right? So we have 1 over x squared plus 1, right? And let's say this is the integral from negative infinity to infinity dx. So what this is we have the real axis here and the imaginary axis here, right? Now, we see that this is the same as 1 over x minus I x plus I. Right? And so basically, that means that you have two poles at negative I and at positive I. So what do we do with this information? What we can do with this information is basically we can actually draw a contour around the pole that we want to solve for. So over here, we want to find the real axis, right? That's what we're solving for. So we can draw a contour like this that's moving in the counterclockwise direction. By the way, remember, counterclockwise is positive, while just clockwise is negative. So, what we can do with this information is do something like this. So what we see is that the pole we're solving for is encompassed in just this area over here, right? We can of course do it the same for the bottom, but then it would be counterclockwise and we would need to change the way we solve for it. So, okay, if that's the case, what do we need? We only need the pole at plus I, right? Which would be this part. So, let's just say x to z, because that's the convention. And then this is the same thing as the contour integral, right? Over this entire hemisphere is equal to the integral of that real axis plus the integral of the top arc. Now the integral of the top arc is really easy to see, it goes to 0, simply because we have 1 over a polynomial, and as that polynomial goes to infinity, as this goes out, as the arc expands outwards, 1 over infinity is just equal to 0. So we don't even need to take this into account. So really we see that the overall integral of the entire system is simply equal to what we want. Okay, so if that's the case, and we know the entire thing only encompasses the pole at positive I, what we can do is essentially we can solve by using the residue theorem. So that's going to be 2 pi I times the residue at positive I. So what is the residue at positive I going to be? The residue at positive I is going to be, the residue at positive I is going to be, give me one moment. It would be, yes. So this is multiplicity 1, right? Since this is multiplicity 1, we can simply use the formula. So we have 1 over x squared plus 1, right? As we can see, 1 is equal to px, right? Which is, of course, not equal to 0. If we plug in I into here, that would get you negative 1 plus 1 is equal to 0. Is equal to 0. So that means that q of x is equal to 0. I apologize, give me one moment. And of course, q prime of x is equal to 2x, which is 2I, which is of course not equal to 0. Oh, I apologize. This actually should be z. Um, I just wrote x over there because I'm dumb. but this should be z. This should also be z. This should also be z as well over here, right? Well, it's z sub k, which is the pole we want. Okay, so basically, since we know this information is true, we can now find the pole, the residue. So it's just going to be px over q prime, which is just 2z at I, which is just going to be since we're looking for the pole at positive I, we can just plug in positive I, right? So we're literally going to have the residue is just going to be 1 over 2i. Now 1 over 2i times 2 pi I, this cancels out, this cancels out, this cancels out, this cancels out. So really, the answer is just going to be pi. So now we know for a fact the integral from negative infinity to infinity of 1 over x squared plus 1 is just going to be pi. So I hope that helped out some people, and I hope it shows how to use the residue theorem. And yeah, thank you for so much for watching my very first YouTube channel video, really. And thank you for paying attention. Have a fantastic day, and thanks for listening.